Thank you for coming. And so let me continue a little bit through what we were doing. So just to recap, we start with this linear model. Essentially, we're estimating the condition expectation of an outcome, the real line, given a vector at RP. And we have random fluctuation around it with conditional mean equals 0 and a homoscedastic model to have conditional variance equal to sigma square. And the idea is that we're going to allow to have many more variables than observations, so have this ill-posed system. But there is a structure in the sense that the number of coefficients, number of variables that matter actually is only S, and that is smaller than the sample size. And which, I briefly discussed the Lasso estimator yesterday, and there we show that the mistake you make in the prediction norm is bounded by 2 times 1 plus 1 over C lambda square root S over kappa C bar, provided that lambda is bigger than C x over n, provided this event occurred where C is bigger than 1. So that's going to dictate the choice of lambda. So that's essentially, this is a measure of the noise of the problem. So we put enough regularization that you can kill the noise, essentially, and then everything becomes about the bias introduced in the estimator. That's dominated rate of convergence. But we also have to deal with the fact that we have too many variables and potentially not a nice identification, and that was this constant kappa.
Can you maybe write a little bit more strength?
Oh. And that looks like a version of the minimum angle value, but is actually only over a restricted set. And where the restricted set is vectors delta in RP, such that the L1 norm outside the true support is bounded by a constant times the L1 norm in the true support. And so essentially, the idea is that your mistake, beta hat minus beta naught, that is delta. So mistakes in the L1 norm outside the support that you care is bounded above by the mistake you make in the true support. Since the dimensionality of the support is small, this set is actually a much smaller set than the whole RP. So let me just quickly kind of give how these statements here generalize for the M estimator case that I briefly mentioned in the end of the class. So in the case of M estimators for a convex loss function, so we'll have some function Q hat. So in that case, the Lasso estimator just becomes the trade of, it's like balancing fit of this convex loss function plus the L1 regularization. And in the case of the least squares, Q hat is simply this piece. Right. But we're going to be able to talk about the logistic regression, quantile regression by having this framework. And then in that case, to try to see how these sets show up, it's actually very similar to the mathematics. By definition, we know that the objective function evaluated at the estimator is no greater than the objective function evaluated at the true value. And then by convexity of Q hat, we know that Q hat beta hat is at least Q hat beta naught plus the gradient of, or some element of the subdifferential of Q hat beta naught, beta hat minus beta naught. So we can minorate the left-hand side even further by this, and plus the L1 norm, and this is the same one of this term, so they can cancel, and then we get the gradient at the true value times beta hat minus beta naught plus lambda beta hat less equal than lambda beta naught. And then we're going to apply similar tricks we did last time, but just with this degree of generality, we have Byholder minus the gradient at infinity norm times beta hat minus beta naught. 1 less equal. Then here we got lambda. So let me lambda beta hat in the support, in the true support minus beta naught. 1 minus lambda times beta hat outside the true support, the L1. We're going to do similar split here, and we're going to use the event that lambda is chosen such that is C times the L infinity norm of Q hat. And this is actually a very important quantity, right? Because the gradient of the criterion function at the true value, that's the score. And this really drives all the statistical estimation. It's really the source of noise that drives you away from the true value. Right? If the gradient at the true value was 0, and you minimize the criterion function, that's where you stop. That's where you get the estimator. So this is really the fundamental measure of noise in your problem. And it shows up in all sorts of estimations. So it's really a fundamental object to keep in mind. But then we assume it's majorated by lambda over C. So we can put it there. So minus lambda over C times, I'm going to do the same split I did before. So we get beta hat T complement 1. I'm going to take this to the other side, plus lambda beta hat T complement 1. Let's equal lambda beta hat T minus beta naught 1 plus lambda over C beta hat T minus beta naught. By collecting the terms, lambda goes away, and then you get, in this setting, in this more general setting, that beta hat minus beta naught belongs to the restricted set. Right? So the mistakes outside the true support are bounded by the mistakes in the true support times a constant. But now this is really the natural generalization of this event. But this really provides kind of a very nice way for you to pick lambda in different settings. So let me now move towards penalty choice. So essentially how to pick lambda. And there are many approaches for that. So, yes?
You mentioned something because yesterday you mentioned the least squares. Right?
Yes.
And so if you're taking p less than n, like yesterday when you began, you could use the same sort of analysis also for this more general complex loss functions, right?
That's correct. Yes. So there will be, so for the least squares, there was this square root p over n rate. When you go for m estimators in general, we're going to have the same type of result under fairly general conditions. Yes. And so this was a crucial event to achieve this restriction, which in turn is the one that gives you identification. And on top is also the key event to control the noise. So the choice of lambda really plays a key role. And the choice of lambda is really be context specific. It's going to really depend on your particular model. So let's just briefly mention what I mentioned last time. So in the very first model, we have our linear model. And let's assume the errors are IID, normal, 0, sigma square, so full normality. And what we want this event to happen with high probability. Or we want, essentially, the probability that the gradient at q hat, beta naught, infinity, bigger than lambda over c, that to be some order of 1. Right? That's what we want. So let's say we want this to be less than or equal than some alpha that we want to control. In the case of these squares, q hat, the gradient of q hat of beta naught, we know it's just x transpose epsilon over n. And this, if epsilon is Gaussian, this is actually also Gaussian, 0 mean, with covariance matrix x transpose x over n times sigma square over n. I have to do the calculations. So if you know sigma, which is assumed in many studies as a first attempt, one can actually simulate this quantity. Because you observe x, you know sigma, so you just simulate a bunch of normals, and then you can pick lambda in a way that this happens with probability alpha. Right? A more concrete, and this actually has an advantage that it will adapt to the covariance structure of x. So for instance, if all the x's have are just repeated regressors, really the dimension is just one variable. So that will definitely adapt to that particular structure. So we end up a very small penalty, which is the right one. But if they're really essentially orthogonal to each other, then you're going to end up being with higher factors. Now, the typical choice people do in the literature, they say, well, this probability bigger than lambda over n is less equal than p times the maximum over j less equal than p probability of 1 over n summation equals 1 to n xij epsilon I bigger than lambda over n over c. And typical normalization in these settings is that the columns have unit second moment. So this is just a rescaling of the columns. So at that point, each of these variables is just a normal 0 variance sigma squared over n. So then essentially this becomes less equal than probability p times. And then this would be 1 minus phi evaluated at lambda over sigma c square root n. Just normalization. So the choice that would make this work is just say if lambda is chosen, like sigma needs to scale with the noise times c divided by root n, and I want the inverse of the cumulative normal distribution of 1 minus alpha over 2p. And there is a 2 here because of the absolute value. So this is some theoretical choice that many papers actually propose under the Gaussian assumption of the noise. And indeed, when you plug in this choice, these terms cancel with these terms. The phi applied to phi minus 1 gives you just the argument. The ones cancel, and then you get, let's see, the alpha. Right, so that's the standard choice. Of course, this assumes normality, and one wants to generalize that to non-normal settings. So a second design would impose some trade-off between tails of the noise and size of the covariates. So for instance, if you have, just for simplicity, uniformly bounded axis, this can be relaxed, but just for and you have fourth moments. Probably can get away with the second moments only, but second moments. So basically, what we want to bound is this, in the case of least squares. And one can just formulate this as 1 over n summation of, max over j, p, 1 over n, xij epsilon I. So that was actually viewed as essentially an empirical process. So basically, people have been applied either Nemirov's inequality or just empirical process bounds. And essentially, we can show that with high probability, there is a constant. This means that there's a constant times square root log p over n. The problem is this approach that gives you this constant. Right, so if you want to use, there will be some constant here. And if you want to use that to guide your choice of penalty, what happens is that this constant is going to be just too big. Essentially, it's going to just zero out everything in any reasonable setting. So this is a good theoretical device, but here you really care a lot about the constants. Like just being off by a factor of 4 means, and you try to estimate if something 4 times higher, essentially zero out everything and you don't get any signal back. So, and now if you want to something precise, then you need to. Oh, the constants will depend a lot actually. First on which tools you're using, right? That will definitely depend on k. With uniformly bounded, we'll have some k here. So this is just with high probability, right? Sorry. No. Sorry. So one thing that provides some guidance is some approach that at least asymptotically becomes sharp. And one way to get something that looks sharp asymptotically will be the following. So first, let me keep these assumptions just for simplicity and work with weaker assumptions. But there are some inequalities for self-normalized sums. And essentially, they look like something like this. And this is from De La Peña, Lai, and Shao. So if I have independent random variables, Z1, Zn, with 0 mean, such that 1 over n summation of third moment and divided by the average second moment square root, that's bigger than L, then uniformly over 0 less than t less than so here n to the 1/6 divided by L mn. I'm going to see where mn, we're going to allow mn to grow, so to shrink this set. We have the probability of summation of zi's divided by square root of the summation of zi's squared bigger than t divided by 1 minus the cumulative of normal at t. This minus 1 is less than universal constant divided by mn cube. So what is it saying? So give me some nice ratio between the average third moments and the second third moments. And this doesn't need to be identical random variables. They can be just need to be independent. But then I provide you with a range that as long as you don't go deep into the details, this ratio essentially behaves as a Gaussian uniformly in the whole range. I cannot make statement about the tail, but in this range, it really behaves like a Gaussian. If the range decreases, as I allow by mn to increase, this goes to 0. So if, let's say, mn is log n, this essentially goes to 0. So we're really getting uniformly convergence in this particular range. So how we apply this to our setting, we have probability of x epsilon over n bigger than lambda over c. And now I'm going to define the second event, which is some uniform convergence for the second moments. So essentially, 1 over n summation of xi square epsilon I square minus sigma square is less than sigma square over log n, let's say. So this can be made sharper, but I just want this uniform convergence to happen. So keep in mind, so this, what's the expected value of this 1 over n summation xi square epsilon I square? Is that xi's are fixed. So basically, this is just 1 over n summation of xij square expected value of epsilon I square. If you want given x, so this is just sigma square. And so you can pull it out. So 1 over n summation of the square of x, that's just the normalization is 1. So this, so essentially sigma square is just the mean of each one of these terms. I'm just asking for the maximum of this deviation to actually go to 0. And there are a number of conditions that apply. This condition certainly implies that with a lot of slack. So these events are going to happen with high probability. So going back to our condition over n bigger than lambda over c, this is going to be at most probability of x epsilon over n bigger than lambda over c, and the second event happening, plus the probability that the second event does not happen. And this is going to go to 0 fairly fast under nice conditions here. And now, so here I can, so this is, I can further bound now by union bound P times the maximum over J of the probability of 1 over n summation xij epsilon I bigger than lambda over C A2 plus complement. Now here, if I divide it by summation of 1 over n square root of xij square epsilon I square, since I only care about the event on E2, I know that this is no bigger than sigma 1 plus log n. You don't have a square root there. It's just some factor that's going to go to 1, actually. And then P, then I can actually let go of the intersection. I take the square root, one of the square root to the other side, and then I have the variables in the format I want, xij epsilon I over root n, divided by summation, square root summation of xij square epsilon I square over n, bigger than lambda square root n over sigma C plus log n half plus. And then we apply the theorem. Precisely. But there is one extra caveat, because we need to ensure that this happens. Right. So the inequality is going to work only if I pick my lambda to fall into on this uniform region. So what that's going to boil down is going to, a side condition is going to show up. So then here the choice is, natural choice will be the same. Very similar, will be lambda to be sigma times C times is 1 plus 1 over log n 1/2 divided by root n phi minus 1 minus alpha over 2p. And then we have that this is essentially alpha plus probability of E2 complement, as we want, but we need to ensure that this part actually has the right, belongs to the right range. So this part, plugging in the choice, square root is going to cancel with the square root. The C is a sigma. This is just a constant. Essentially, we get phi minus 1 minus alpha over 2p. This needs to be smaller than n to the 1/6 divided by Lmn. That's the condition. Now, indeed, if I am in a situation that my x grows, this third moment potentially grow, so this L is going to grow as well. here is where it's going to show up. I'm not going to be able to I'm going to have conditions precisely on P. These we know can be bounded by essentially square root log to P over alpha. We have a 2, we have essentially a constant here. So this essentially is what we want to enforce. So essentially the condition that this requires is that log P to be little o of n to the 1/3. So that condition allows us to pick the penalty parameter for situations in which I only have potentially third moment in the precise same way we pick parameters. We pick lambda for the Gaussian case. Right? And these are the same constants. Right? And this is what we actually see in simulations. Right? We see that that penalty choice is actually a very good one, and I think it's something like that. So this is good, but one can actually potentially do better. Essentially, I should expect on top of that, so here every coordinate is converging to a Gaussian. But I could even think that they are converging to Gaussian jointly, right, in the L-infinity norm. And there has been a few results that are actually studying that now. You're going to pay a price. Right? So here we paid a price that before consistency could be achieved by S log P over N, which means essentially log P needs to be small compared to N. To deal with heteroskedastic cases, we're asking for log P not to be bigger than N to the cube. If you want to take advantage of the structure of the axis, that if they are very similar, highly correlated, you don't need a bigger penalty, but you want a joint convergence, the conditions that are showing up are something like log 7P or N. So that's kind of the less bounds I'm aware of. And that would allow you to actually simulate directly through some Gaussian, if you have homoscedasticity. But all these ideas also go through heteroskedastic models, if you have kind of iterative schemes. But this already takes you fair into the nice choice with very good constants. This,
Let me ask you a question. So you said that this lambda is from the right lambda if you look at simulation, right? But do you see some sort of restriction on P coming up in the simulations? That you need to
well, it's a trade-off between P and the tails of the noise. When you start taking heavy tails, like variable, like if the error is like T4, then you see that things start, this doesn't work anymore, this type of approximations. It does show up. But if you run simulations only with the Gaussian noise, then you don't see any of that. That's the issue. So this was for the least squares. Let me mention the other models. And so if you let's go to, let's say, for the logistic model, logistic regression. In that case, we model, so yi is actually either 0, 1. So we're actually modeling the probability of yi equals to 1 given x, which is just expected value yi given x. It's modeled through the logit function, x beta naught, and the logit function of t is just expected value, exponential of t divided by 1 plus exponential of t. And this is probably the nicest function you can wish for in your life, because everything works. It's like a super nice function, infinitely many times differentiable. The derivatives are always bounded by 1. It's like everything you could wish for. It's self-concordant, so you can do actually a lot of interesting things with it. A version of a log of that's below self-concordant. And so if, in this case, if you want to make estimation, right, in the likelihood would be the product across observations of the probability when you do of b equals to 1. So observations that you saw as a 1, you take the logit function, you consider logit function. But if you had a 0, you consider 1 minus the logit function. So that would be the likelihood function. One likes to maximize likelihood function, but we're dealing with minimization, so we're going to take logs and then minus of that. So our q hat of beta would be minus 1 over n summation of yi log of xi of gamma x beta plus 1 minus yi log 1 minus x beta. And after you are done with the manipulations, because of this structure, you get 1 over n summation over I log of, no, I forgot. So it's going to be, I think, 1 plus exponential of x beta minus yi xi beta. After you're done with all these, is that correct? Yes, that's what you end up with. So that's the criterion function. Now all we need to worry about is the gradient of this function at the true value. And we want the infinity norm of that. So the gradient becomes 1 over n summation over I. So here it's going to be minus y times xi. So there will be a vector xi minus yi. And then here we get literally the logit function x beta naught. Just because take the logs, these go in the denominator, then take the derivative of that, you get the exponential on top. That's precisely the logit function. So what's happening here is that for every observation, the expectation of the y's is precisely this. So each term is 0 mean. So again, you have a sum of 0 mean variables. But on top of that, this part here, this is between 0 and 1, and the logit function is between 0 and 1. So this is actually bounded between minus 1 and 1. So now you can do Hoffman type of inequalities and get exponential type bounds. So the probability that the gradient at a true value is bigger than lambda over n c is less equal than p max over j, probability 1 over n summation of xi beta naught minus yi xij bigger than lambda over c. And this becomes P max over J, that's equal to P. And then just some Hoffman inequality, you get 2 times exponential of minus lambda over C square n divided by the sum of 1 over n xij square. And then this square can be bounded by just 1. And this normalization we were assuming to be 1 again. So the choice of lambda that would work here would be just C over square root n square root of, there's a 2 there, missing, 2 log of alpha over 2p, which is kind of a Gaussian type of concentration. One can also apply this similar ideas of the self-normalized model deviation here. You can get essentially what you can deal with is that the variance of this term is actually smaller than 1/4. So under some conditions, you can actually get by diminishing lambda by a factor of 1/2 further. And just in the last 5 minutes, let me just mention the quantile regression case. So there, y equals to x beta tau, so the coefficients depend on a particular quantile interest, plus the error term. And the error term is such that the tau quantile of the error term given x equals to 0. So the probability distribution of epsilon given x at 0 equals to tau. And that's kind of the condition. And so what's the Q hat function of beta here is just 1 over n summation, what they call the check function of y minus x beta. And the check function is this function that penalizes symmetrically. If you make, so this is rho of tau. If you make deviations to the positive side, for here, if here's one, so the angle here, the tangent will be tau. But for the negative side, the tangent will be 1 minus tau. It penalizes a symmetric penalty. So basically, the rough idea is that if you have the tau quantile 0, it means that a fraction tau of the time you are below 0, and then you get a penalty of 1 minus tau. So the expected penalty here is tau 1 minus tau. And a fraction 1 minus tau of the time you are positive, with penalty tau becomes tau 1 minus tau. So kind of balance both of them. But this is a symmetric penalty does the trick. And if you want to do the choice of penalty here, we just take the gradient, but this is not differentiable. But all that we need when you look at the proof, we just need one subgradient. So we don't really care. So as long as we can write down a nice subgradient, we are good to go. And it turns out that we can, because so 1 over n summation. So this is a function that if it is negative, the slope is 1 minus tau. So essentially, it's going to be indicator of y less equal than x beta minus tau x. So that would be a subgradient of that function. And I might need a minus sign there. But since I'm concerned with the true value and the infinity norm. That's what we need to control. Now, there is one at the true value. Now, the interesting thing about only worrying about this at the true value is that, so this is everything conditional on x, which means that the only thing that's really random is the y. So, and this is a binary variable. What's the probability that the y is going to be below its tau quantile? It's precisely tau. So it turns out that so expected value of indicator yi x beta tau is just the probability of y, let's equal to x beta tau, which is equals to tau. That's the quantile definition. But there is one more trick that makes things very convenient, is that this random is a random variable now. It actually has the same distribution as the random variable ui, let's equal to tau, where ui is just uniform 0, 1, independent of x. So distribution-wise, they are the same. So the distribution of my score is actually pivotal, and completely pivotal. So I can actually simulate just this quantity up to any precision I would like, and I can get the quantiles of that to pick my lambda. And this will take care of any correlations between the x's. If the x's are all the same, these will be very small. If the x vary a lot, these will be bigger, but I will fully adapt to this to the score by doing simulations. So this is the case I have 1 tau to estimate. And that's how the proof would go. Now, if I want to do more than 1 tau, essentially a whole range of taus, what happens is that when I do this argument, I'm doing one argument for each tau. So I want this event to hold for each tau. So what I really want is lambda to be bigger than c times supremum over taus in the range I care. And here will be a subgradient. And this I can also simulate. As long as I use the same UIs for all taus, that's exactly the same distribution again. So this choice I can definitely simulate, takes full advantage of correlation structure. And now is where it's actually to get rates of convergence, it makes sense to use empirical process type of techniques, because then this is essentially a continuum of functions. I can take the supreme of that, and I don't care about constants in my bounds. I care about my constants in my penalty choice, but the penalty choice is actually driven by this simulation, so that becomes sharp. There is one or two little tricks that it's convenient because these terms, they have different variance across tau. So it's actually convenient for you to normalize by square root of tau 1 minus tau. And then when you apply for the penalty, you actually use this lambda times square root tau 1 minus tau. So it's a lambda is a tau specific penalty choice, but the lambda needs to hold uniformly across all tals. So that makes the bounds tighter. And then one can show that these will be bounded by a constant times square root log p over n, depending on how these guys grow. If these limits go too close to 1, then an extra term is going to show up here. But essentially, this framework of M-estimators makes it very clear what's the key quantity for you to achieve the restriction. And then once you go for the specific application, you have a very clear guidelines of how to get a condition. I think the combination of simulation or self-moderate deviation gives you very close to sharp bounds. Other choice of penalties that could be data-driven, it would be cross-validation is one of them. Those have some issues from the theoretical perspective. They're still not fully understood. The proofs I'm aware, they make strong assumptions to get something, and I don't particularly believe those assumptions in many applications. There is also the slope heuristic. Though both choices, they try to fit the data well, so they tend to be smaller than these theoretical choices. So these theoretical choices tend to be a little bit more aggressive in trimming them. It has advantage and disadvantage. For rates of convergence is the same, but if you care about post-model selection estimators, these type of choices trim more, you tend to have a better behavior after. And that's what I will probably going to start talking next class, is to talk about what happened after model selection and what you can get in terms of rates and then confidence intervals. And I think I'm already over time.